Hello there, welcome to the Learning of Engineering tutorial video lectures. In this video lectures, we are trying to discuss about the torque transmission in terms of the polar moment of inertia. And so far that we have seen the torque transmitted by the governing equation. What is that? That equations we have calculated that T is equal to 5 by 16 tau into d cube. And this is the power transmissions we have calculated. So here is the tau is going to be the maximum shear stress that is existed on the outer surface of the shaft. So then how could you, that I want to find out the torque transmission in terms of the polar moment of inertia. As we know, the polar moment of inertia, it is going to be taking in terms of suppose. So there is going to be I am going to be indicated letter with the J here, that the J is nothing but the power transmission, that means the polar moment of inertia, that is equal to, I am going to be considering Ixx plus Iyy. So in this case, Ixx is the moment of inertia with respect to the x-axis, and Iyy is the moment of inertia with respect to the y-axis, and the Ij, or I can say that is going to be the Iz, that is going to be the polar moment of inertia with respect to the z-axis. So this axis is perpendicular to the remaining these two. So then how could you find out that the torque transmission in terms of the polar moment? So as we know that we have considered there is a circular shaft we have taken, right, that is a cross-sectional shaft. Then we considered one elemental strip, so that whatever the force is going to be coming to this one, that we are taking the integration for the total shaft. So in this case what will happen, this is going to be the R, right? So R is going to be the location of this one, and the dr is going to be the thickness of this elemental ring, and this is going to be the capital R we do have. And similarly we know the formula is going to be, so that's going to be tau by R is equal to Q by small r, that's going to be C theta by L. So by using these equations we will try to find for the torque transmission in terms of the polar moment of inertia. As we know, so this member is going to be subjecting, that is going to be the dt is going to be the torque transmitted by the elemental ring, that is equal to, that's going to be dF is going to be the torque force into the radius we are going to be considering, right? So how could you find out the dF? So from these equations I am going to be finding, so that dF is equal to, as we know, this is the tau is going to be the maximum shear stress existed on this outer surface, and the small q is going to be the torque is going to be that is the shear stress is existed on this elemental. So that's from this equation the q is equal to tau by r into small r I am going to be considering. So then we know this is going to be the shear stress. So that equation I am going to be writing q is equal to dF by dA I am going to be taking. So now I am going to be taking the dF. So from this equation the dF is equal to q into dA I can write. So the same equation I am going to be writing over here. So that is going to be the q dA into r I can take it. Right? So then what is the Q? The Q is nothing but the shear stress existed on your elemental strip. So that I can write in terms of the maximum shear stress and the outer radius and the location of the elemental ring. That's going to be tau by capital R, that is going to be small r, dA into r I can take it. From this one again tau by r is equal to r square dA I can take it. We know this is going to be the dt. This is the elemental ring is carry forwarding the torque. So then what I am going to do? I am going to be taking the integration 0 to t, and here is going to be 0 to r something I can going to be considering. Right? So then once I am going to be substituting in this equation, this tau by r is going to be the constant, and this will become the t. The t is equal to tau by r is equal to, tau by r integration 0 to r square dA I can take it. So we know r square dA is nothing but, so when we are going to be taking, this is going to be calling your polar moment of inertia. So that we are going to be calling the polar moment of inertia. The T is equal to tau by r into j, we will get it. Alright, so the J is nothing but integral r square dA, we will get it. So then we can say that is going to be the polar moment of inertia. This equation I am going to be simplifying. T by J is equal to tau by r, that's going to be c theta by L, that's going to be q by small r. So this will become your governing equation where we can find out the unknown parameters from here. So it means that the torque transmission of a shaft we define in terms of the polar moment of inertia. In a questions, suppose there is a polar moment of inertia is going to be coming, so these equations are not going to be valid. So then what happened? Again we are going to be using this one. So this mathematical model will help to find out the torque transmission in terms. In this case, suppose there is a given the torque and shear stress as well as the radius of that shaft. Then we can calculate the polar moment of inertia of the particular shaft, we can calculate it. So I hope you are able to understand the torque transmission in terms of the polar moment of inertia. So thank you.